All right, now we're looking at a one-dimensional motion problem with two different objects moving in the same time frame. So this example here was taken from a textbook called Physics for Scientists and Engineers, 6th edition by Paul Tipler and Gene Mosca. I'll put a link in the video description in case you're interested in purchasing this textbook. There are later editions of Tipler and Mosca, but I think the 6th edition is the best one. The later editions, they made a number of changes to the example problems, which to me seems more confusing in their solutions. I like the 6th edition the best. All right, so anyway, this example. We have two trains face each other on adjacent tracks. They are initially at rest, and their front ends are 40 meters apart. The train on the left accelerates to the right at 1 meter per second squared. The train on the right accelerates to the left at 1.3 meters per second squared. So part A, how far does the train on the left travel before the front of the trains pass each other? Part B, if the trains are each 150 meters in length, how long after they start are they completely past each other? All right, so next we want to set up a number line and draw a picture. So to approach this solution, we set up a number line and locate each train with the front of the left train at x equals 0 and the front of the right train at x equals 40 meters, because we know they're 40 meters apart. Then we write the equations of position for each train and set those two equal to each other, because we know that when two trains meet, they're occupying the same position. Then find the time when they meet. Once we know how long it takes for them to meet each other, then we can put that time into the position equation for the left train, and that will tell us how far it traveled. Now for part B, we do the same thing, but now we locate our origin at the back end of the left train. And we'll mark the back end of the right train, and then when the back ends are at the same position, that's when they pass each other. All right, so here's the position, or the diagram that I've drawn. I have the train on the left, I mark that L, and the train on the right, I mark that R. So I've got the front of the left train, I set that equal to 0, that position equals 0. Since the right train is 40 meters away, its position is 40 meters. Then I have the equation of motion for the train on the left. It's starting from rest, so initial velocity is 0, its initial position is 0, so the position as a function of time is just the acceleration term, the 1/2 at squared. Now for the train on the right, his initial position is 40 meters, his initial velocity is 0, so I don't have a vt term, and for his acceleration I got negative 1/2 at squared. Why the negative? Well, because he's going to be accelerating to the left. Right? His acceleration, he's going to be speeding up in the leftward direction, so the acceleration will be to the left, and we're calling right positive, left negative. All right, so now I've got the position as a function of time for the left train and the position as a function of time for the right train. So they meet each other when those two positions are equal. So I set xl equal to xr and solve for t. That will give me the time that they meet. Once I know the time that they meet, then I can plug that into the x sub l equation and get how far the left train traveled in that time. Okay, here it is with the numbers. So they meet when xl equals xr. So I got 1/2 a sub l t squared equals 40 minus 1/2 a sub r t squared. And I put the t squared terms together. So I have multiply both sides by 2 and put the AR t squared term on the left side. So I got AL plus AR quantity t squared equals 80. And then divide both sides by AL plus AR. And then take the square root. So I've got 80 over AL plus AR and then square root. Well, AL is 1.0 and AR is 1.3, which gives me 2.3 meters per second squared. So 80 divided by 2.3 and then square root, I get 5.9 seconds. So that's how long it takes for them to meet. All right, now to get the distance, how far the left hand traveled in this time, I've got its position 1/2 AT squared. So the 1/2 is the 0.5, the A is the 1 meter per second squared, and the time is 5.9 seconds, but don't forget to square that. And when I crunch those numbers, I get 17 meters. So the left train traveled 17 meters, and when they catch up to each other, when their fronts meet. Now the next part of the question, we want to find how long does it take for them to pass each other. Well, now we've done this part, that should be easy. All right, now we want to get part B of this problem. If the trains are each 150 meters in length, how long after the start are they completely past each other? Well, the trains pass each other when their back ends are occupy the same spot at the same time. So again, we just draw a diagram, but this time I'm going to move my origin at the back end of the left train and call that position x equals 0, because now we want to look at what happens when the back ends are at the same spot at the same time. So my origin is the back end of the left train. I'm calling that x equals 0. And then the back end of the right train will be at 340 meters. Now remember, the trains are 150 meters long. So I've got 150 meters to go from x equals 0 to the front of the left train, plus another 40 meters to get to the front of the right train, plus another 150 meters to get to the back end of the right train. So 150 plus 40 plus another 150 gives me the back end of the right train at 340 meters. Now I just write the equations for the positions as a function of time for each train. And notice that these are the same equations we had for part A. The only difference is the initial location of the back end of the right train is now at 340 meters. So for the left train, we've got x sub L equals 1/2 a sub lt squared. And for the right train, we got 340 meters for the initial position minus 1/2 a sub rt squared. Now the trains pass each other when these two positions are equal. So I just set x sub L equals x sub r and solve for the time. And that will give me the time when the ends of the train are at the same location. Now I won't go through the algebra and plugging in the numbers, since this is exactly the same as what we did for part A. So I'll let you do that as an exercise for yourself. All right, so that concludes this example. So I've done several examples now for motion in one dimension where we're just moving horizontally. So now we'll do a few examples of up and down one-dimensional motion where we're going to include the acceleration due to gravity. Hi, Dr. C here. Thanks for viewing this video, and please help support this channel and subscribe. Also, please leave your comments, questions, or suggestions, and I thank you for your support of this channel. I've also included a link to the next video in this series.